Hello. In this video, I will present an intuitive overview of the MOS transistor, a very simple overview. And of course, later on in this course, we will go back and examine things in great quantitative detail. The material that I will cover this week comes from the first chapter of the book, but I would like to warn you that it is out of order. In particular, the material in this video can be found near the end of chapter 1. So here you see a simplified view of the MOS transistor. It is built on a so-called P-type substrate, P-type meaning that it has a lot of positive mobile carriers, which are called holes, and which we will discuss later on. On top of which we diffuse two N-type regions. N-type meaning that they have a lot of negatively charged mobile electrons that are free to move and conduct electricity. Between the N and the P, we form p-n junctions, and as you go from the source terminal to the drain terminal here, you can see that there is no path through which the carriers can flow initially. Later on, we will create a path for the current to flow. The length of this region, which is called the channel, will be denoted by L, and the width of this channel will be denoted by W. On top of the P-type region, we have grown an insulator, typically silicon dioxide, and often referred to simply as oxide. And on top of that, we have a conductive region called the gate. Typically, the gate is much taller than what I show you, but for economy of space, we will show it as a shallow region. The acronym MOS stands for metal oxide semiconductor. It originates in the old days of MOS transistors, where the gate was made out of metal and the insulator was made out of silicon dioxide, and the rest, of course, is the semiconductor, which is silicon for us. These days, the gate is not necessarily made of metal and the insulator is not necessarily made of silicon dioxide, but the name has stuck. Another acronym we will be using is FET, standing for field effect transistor, because as you will see, the transistor action is due to electric fields from the gate to the channel region. And sometimes we'll combine the two acronyms and call the MOS transistor simply MOSFET. The MOSFET can be very small. For example, it can be 100 nanometers on a side. To give you an idea how small that is, take into account that the human hair has a diameter of about 0.1 millimeters or 100 micrometers, which simply means that in one diameter of the human hair, you can fit about 1,000 modern MOS transistors. So this is the reason you can have millions of transistors on a chip. The W and L dimensions, this one and this one, for us will be the actual dimensions of the final fabricated device. And I have to say this because when you design the transistor, you're looking at a computer screen and you specify the geometric dimensions on a so-called mask, which are WM and LM. But when you fabricate the device, certain distortions take place, denoted here by delta W and delta L, and the final fabricated device has width W and length L. It is these two dimensions that we will be using in this class. So now here you see the MOS transistor biased in a common way. We have shorted the body or substrate to the source, as you see here. And then between the drain and the source, we apply a positive potential, positive voltage VDS, drain source voltage. And to the gate, we apply a positive potential with respect to the source, VGS. And if VGS is large enough, positive charges accumulate on the gate, as you see here. These positive charges attract negative charges consisting of electrons below the insulator. So now you have an N-type region which has plenty of electrons you have another region in the channel which has plenty of electrons, and finally a drain region with plenty of electrons. So this has formed a bridge between the source and the drain, and current can flow. Because you have connected the voltage with a plus here and the minus there, the electrons will be flowing towards the plus of the battery, but negative charges going like this are equivalent to positive charges going like that. So if you define a drain current in this direction, then this current will be positive. Of course, if you increase VGS further, you're going to place more positive charges on the gate, which will mean more negative charges in the channel, and therefore the current will increase. So the current versus the drain source voltage, this voltage here, if you plot it, goes like that. And if you had a larger VGS, then it could go like this. This region is called non-saturation to distinguish it from this region, which is called saturation. And we will be discussing why the current tends to saturate like this. Now, as we said before, the body is p-type, which means that it has plenty of positively charged carriers called holes. But of course, the positive charges on the gate have attracted negatively charged electrons in the channel. So you see negative charges in a p-type region, which is the opposite from what you expect. This is why we say that inversion has taken place. And depending on the value of the gate source voltage, you can have a weak inversion, or moderate inversion, or a strong inversion. So there are three regions of inversion. We will discuss each in great detail in this course. Let me now give you an intuitive fluid dynamical analog for the operation of the MOS transistor. I start with strong inversion. Here is a repetition of the circuit you just saw on the previous slide. And here is the IV characteristic for a given value of VGS. This is the fluid dynamical analog I was talking about. So the source region here corresponds to a tank over here full of water. And the drain region corresponds to another tank of water, again full of another tank full of water. In between them there is this separator that in the position shown prevents communication between the source tank and the drain tank. I have a handle on this separator and I can move it up and down. Now in interpreting what I'm about to say, keep in mind that water level corresponds to potential energy. And the way potential energy varies for an electron is in the opposite direction that potential itself varies, because the electron has a negative charge. So lower levels of water mean lower potential energy, but higher potential. The distance between the source level and the handle corresponds to VGS. In other words, it corresponds to the voltage over here. This one corresponds to this. Now, I lower the handle, which means I increase VGS, and now water can flow both from source and drain and fill the channel area. This corresponds to the channel being filled with electrons. However, because I have the same level of water in the source and the drain, after the channel fills with water, there is no net movement of water anymore. To make water flow, I'm going to lower the level of the water on the drain tank. So I lower the level compared to the level at the source. This distance here corresponds to VDS, which is this quantity over here. And now you can see that water will flow in this direction and go into the tank. If you have very large tanks, or if you connect externally a pump that maintains the water flow, you can achieve steady state in which, during which water will keep flowing from the source through the channel towards the drain. And you can see that if you increase this distance, VDS, there will be a larger difference between this level and this level over here, and therefore more water will be flowing. This corresponds to the fact that when you increase VDS, the drain current increases. But if you do it If you continue doing this, and if you keep increasing this distance, for example here, and you bring the level of water to such a low position that it is below this level over here, then all of the water that can enter the channel region will spill over to the drain region, and any further decrease of this level will not affect the total water flow. So that's why you reach saturation for the water flow, which corresponds to the saturation in the current. I continue the fluid dynamical analog. I showed you what strong inversion is like. Now, weak inversion corresponds to this. Rather than having fluid flowing, you actually have water vapors flowing. So above the surface here at the source, there are water vapors, and the density of these vapors decreases as you go up, and the same happens over here. If the levels here at the drain and the source are different, you have denser water vapors here than you have over there, so there is a diffusion of water vapors through the channel. And in fact, as we will see later on, in a weakly inverted MOS transistor, even the electrons flow by diffusion. Finally, moderate inversion is something between strong and weak inversion, and it corresponds to a little fluid flow and also vapor flow. And in fact, we will see later on that there is something very similar happening in the MOS transistor. So let's go back to the circuit and plot now the current ID versus VDS using VGS as a parameter. So for each value of VGS, we plot one of these curves. The larger the VGS, the more the electrons here, and the larger the current. So you go from one curve to one above it, and so on. It turns out, for a typical set of parameters for an MOS transistor, that practically all of this region is strong inversion, and you do have moderate and weak inversion, which is compressed near the bottom, and you cannot really see it. So instead of plotting on a linear scale, I will plot the drain current on a logarithmic scale, and now things look like this. We have expanded the low current region, and now we can clearly see the weak inversion region here, the moderate inversion region, and finally the strong inversion region. In fact, we have such resolution for low currents that we can even see a region affected by leakage. And by leakage, I mean the leakage current of this junction. The PN junction here is reversed biased, and there is some leakage current associated with it, which we will discuss later on. So in this course, we will learn to predict the shape of these curves under a variety of conditions for each separate region of inversion. And we will derive models that actually predict the whole thing in one single piece as you go from weak to moderate to strong inversion. In this video, we saw an overview, an intuitive overview of the MOS transistor, and we used a water analog to give an intuitive feel for the regions of weak, moderate, and strong inversion. In the next video, we will look at some realistic MOS transistor structures in popular fabrication processes.